So I'm already sharing my screen, so let's move on from this. And the next session, and by the way, thank you very much, Vivienne. And we should be doing more sessions related to this because this is very, very interesting content and content you should be using today. But tomorrow, tomorrow in the future, we should be using quantum as well. So that's our next session, which will be talking about quantum for a bit. Now, first of all, I need to mention a few things. I have a cat. My cat is sleeping down there, but my cat is very big expert in Azure. So every time I talk about Azure, for some reason, and I do a demo, my cat shows up. So this is my cat. Very important to mention. And one of the things I usually try to do, and sometimes in person, sometimes remotely, is to actually do some crazy sessions that have a lot of different weird themes, but hopefully they are a bit more interesting than just doing some basic sessions. And in our case, because we're talking about something which is very theoretical, apparently very complicated, I want to keep this very simple to everyone, because if everyone is able to understand, I will also be able to understand this, because it's rocket science complicated, but let's make it simple, because all of us would like to use it in the future, and to do that we need to make things simple for someone in IT, not for someone in physics. So this is the next session. We'll talk about quantum and anything related to quantum computing, quantum optimization. We'll talk about all of that just now. So you probably noticed what this couch is actually all about. This is related to some show, and everyone is welcome to sit here except in the reserved spots and actually try out quantum, right now. But we'll probably only use it, really use it in maybe a few months, a few years maybe. But it's important to mention that it exists already. A lot of providers, including obviously including Azure, are able to use this, and this is how we should start the session. Now, my name is André Melancia. This was mentioned before. I come from Lisbon, not that far away from Vivienne, and yeah, let's do this session. By the way, my contacts, just go to wendy.pt. All of my contacts are there. Basically, very simple links to social networks, to LinkedIn, etc. Feel free to contact, and let's see what happens. So I did promise that this session would be very simple, so you don't need this intelligent level. No one has this level of intelligence. It's just too much, so please don't worry. By the way, I didn't mention this before, but if you are available here in the chat, feel free to ask questions via the chat to me or to Vivienne for the session before, and we will be happy to answer all of your questions. If you do that on Facebook as well, there was a slight delay in the sharing, but maybe we'll be able to see things on the other side as well. Okay, so you don't need to be this level of intelligence. You don't also need to be this level of intelligence. This is probably considered one of the smartest persons ever for humanity. So you don't need that, and you don't need to be as intelligent as this guy here. So if you don't know who he is, you should. This is also a very famous physicist, but also a very famous communicator of science. So if you haven't seen him, or if you haven't seen any of his videos, you should. They are very intelligent. They are to human level, not superhuman, super intelligent level, so anyone can understand his videos, which are shared online at some point in time. He died somewhere in the 80s, but his videos are still amazing to understand a lot of concepts about physics, etc. And specifically, it's not accidental that I put this information here about this book. Surely you're joking, Mr. Feynman. Although it says introduction by Bill Gates, which is more recent, for the most recent version of the book, I've actually read the original maybe when I was about 14, 15 years old. It's very interesting. It talks about a lot of different things. It talks about life, it talks about technology, it talks about physics, but it also talks about how to hack safes, real world metal safes, how you do that using social engineering. So this was done already in the 40s. So see this book. I highly recommend it. I was 15 when I read it, and I completely understood it, so no problems there. Anyway, the level of intelligence we all need is nothing like this. These are very intelligent people, but we need this kind of intelligence at this moment, okay? So I think everyone will be able to follow along with this, no problems there, okay? Anyway, let's talk about what we had before. So when I was talking to Vivienne just now, I was talking about what existed, what exists now, and what will the future be. And in the past, we had things like, counting with fingers, like 1, 2, 3, 4, 5, etc. So this was very basic, thousands of years ago. And then we created something called the abacus that had a lot of small balls, like 10 in a row, etc. And we would be able to count with that. So that was our first real, counting machine. But then we move on to mechanical machines. So if you go to some shop, older shop, something that's at least 50 years old, you'll probably see a mechanical, register machine where you get the bill and maybe you get some paper coming out, etc. It has a lot of, digits that you can enter, and that's fully mechanical. So you know that those things actually existed at the time. But then we moved on, and maybe, I don't know, 50 years ago, maybe a bit longer, we moved on to basic electronics. We had things like, vacuum valves and things like that. But then those were very basic. You had things like logic ports. You had things like adders, to sum two numbers, etc. But then we moved on to things like chips. And these chips are very easy, right? If you've taken electronics, if you are from the area of computers or electronics, you'll probably have, in the first or second year of university, you probably have a subject related to logic ports, digital systems, etc., so that you can understand what an AND port is, what an OR port is, and not others XOR, etc. So you'll probably understand how these things actually work. But this, evolved a bit, and then all of the computers turned into big chips. Nowadays, you have, you have things like 386, 486 Pentium, and then you have the i5, i7, even i9 CPUs, which are very advanced, and they are allowed to do a lot of different operations in parallel, etc. So the things, after a while, maybe 10 years ago, something like that, we started to have a problem, which is we cannot speed up things anymore. So when we come to the limit of about 3 gigahertz on a CPU, a bit more maybe, unless you really cool it with, liquid nitrogen and things like that, you're not really going to be able to accelerate it any further, right? So you have to be intelligent. And some computers like, Pentiums started to use some pipelining so that you can run two operations at the same time, etc. So a lot of operations in parallel so that you can speed up your processing. Okay, again, not enough, so we need a bit more. Now, one of the things that shows up after we've created CPUs and even GPUs, graphics processors for games and even for things like machine learning and artificial intelligence, we actually started to use maybe about 20 years ago, but only about 5 years ago have we really started to use that in the industry, right? It was very academic 20 years ago. 10 years ago, some people started to use it, and 5 years from now, 5 years ago, even less maybe, people have actually started to use all of this in their own industries. And that's machine learning, that's artificial intelligence. Everyone knows that this is the future. Anyone who works with computers as a developer knows that they will have to learn this at some point in time. This is, very normal stuff, but this is acceptable. It's very easy to learn machine learning, very easy to understand artificial intelligence, how these things work. And maybe if you work in a company that has this kind of projects, you will be able to play around with this kind of thing, right? But let's have a look at how a few more things work. Now, this is still not enough. If you do a training like for, I don't know, a week based on, I don't know, a petabyte of data, after a week, you'll be able to process all of the information so that you learn from all of the data. And in the future, you'll be able to do predictions based on that data, right? So let's say you read information from, 1 million people that you have as client for our organization, and then you need to extract, some intelligence level coming in from machine learning, etc. You need to extract that level of intelligence so that you can predict what people expect in the future. And these are things like, can be as basic as you go to YouTube and they recommend videos for you. It's not just based on the videos that you saw. It's actually based on some trends that you see the videos, how long you see them, if you repeat seeing them, etc. There's a lot of different factors that go on here, but that requires time. And this is our problem here. It requires a lot of time to train all of this information, right? So Vivienne was actually mentioned that we receive a lot of information in real time. If it's an IoT device, you might also be able to extract knowledge from that information. And if it comes in real time, it's going to be very difficult to process all of that at the same time, right? So we need something else. And quantum comes along, right? And quantum seems like the next best thing. While in things like a normal CPU, you would have, let's say, process things for a whole hour. In quantum, it can be as fast as just a few minutes, okay? Now, quantum is not as advanced as we would like. So it's not going to be, I don't know, 100 times faster, 1,000 times faster just now, but it might be in the future. It probably will be in the future. So what's the difference between quantum and this? How do I actually use it? Okay, and now that is simple. So first of all, in a normal computer, you have bits and bytes, right? You have zeros and ones. This is all very simple. But in quantum, you have something called a qubit, okay? No matter how you read qubit or qubits or whatever way you want to read it, it's a qubit, QU bits, right? So you have to understand what it is. It's still zeros and ones. So in the end, you'll use zeros and ones. But in reality, it's not just a linear number of 0 or 1, right? It's actually more of a multidimensional model where you have some particles that show up in different positions, okay? And these some examples are actually down here in the sofa that you see here in the bottom, right? You actually have like a 3D model of what a qubit is. Let's say if it points up, it's 1. If it points down, is 0, or vice versa. But what if it points diagonally? Which value is this? Well, it depends, right? There was a convention here. Someone will do it. From our point of view, it doesn't really matter. You don't even see the bits in a normal computer. You just see a CPU. You assume everything works there. And on quantum, it's going to be the same thing. Let's say you have a cloud provider, which can be Azure or something else, and they will be able to handle all of those bits for you. All you see is some programming on the outside. And this is what you want. You need to understand how the programming works so that you can do operations with it. Okay, now a few more examples. Well, in a bit, you have something like 99% certainty, or you only have like 1% of error in some cases, right? You do have errors. It is normal to have errors in, passing data, etc. But most of it is usually correct. It's easy to get or 0 or 1. There is no midway. There is no big conflict. It just works in most cases, right? Plus, on a slightly higher level and then higher level and then higher level, there are validations. There are CRC, check, recheck, check, checksums, etc. There's a lot of different techniques to guarantee that even if the normal bits are wrong, they will still be fixed on a retry, etc., and things will still work. Now, with qubits, the uncertainty is much bigger. That's why sometimes people run the same operations multiple times, and then statistically, like let's say 10 times, 100 times, and then the result that comes out of them, they choose based on probabilities. So if the result is going to be 90% that's a 0, or that's a 1, that's going to be the one that's correct. But still, you have 10% of wrong options. And that's because when you measure it, there's some uncertainty with measuring, quantum level, really small stuff. Okay. Now that happens. Please don't worry. But we'll see some techniques how to fix it. Okay. Now, reading a qubit, as you probably heard from Heisenberg's uncertainty principle, you cannot see the speed and you cannot see the position at the same time. You either see one or the other. You can estimate them, but if you try to read one, that will fail the other one, right? So that's a big problem right there, which we have some difficulty understanding, right? And this is not a problem for you or me. We work in IT. It's not really our problem, but it is a problem for someone who designs these systems and has to, sort out the bugs in all of this, okay? So anyway, There's weirder things. So there's you can talk about Heisenberg's uncertainty principle, but there's also other things that come into play. I'm considering things like Schrodinger's cat. We don't know what the bit is going to be until we actually read it. But the problem is, once we read it, it becomes invalid. So how do we fix it? It's not like a normal computer that we can read the same bit over and over again. There are some nice techniques to handle this, so that on a higher level, when us humans play around with this, it actually works pretty much the same as a computer down there, but obviously much faster, okay? So there are libraries for this. Let's move on and understand how this works. So first of all, usages for artificial intelligence and machine learning, it's getting information, processing the data, using things like synapse analytics, etc. And this actually allows you to play around with all of the information, learn some more from the information, and then, get better, results for your clients. And in the end, you get more money. So that's, pretty much everything in this world revolves around money. So you get more money if you get better results for your clients. And this is how it works. But it also costs money to process things in machine learning. So quantum should be a bit cheaper, right? At this moment, it probably won't be, but in the future, it might be in the future that, a simple computer can be as small as a small watch. It already is, but, for big computing, and it becomes smaller and smaller every time. We don't know this, but, we expect this to happen within a few years, within 1 or 2 decades. Everything will be extremely small. Right? So for quantum, this is our expectation. We expect things to change. Now, what kind of things do you use in quantum? Well, there's optimization. So things like, let's say you have a road like a map or something like that. You want to get from A to B. You want to find out what's the fastest route. You don't just figure out what kind of traffic you have there. There's more intelligence that goes on, because when you move from A to B, if you arrive at the middle, you've already spent, let's say, 10, 15 minutes, and then the traffic changes, and then you have to recompute. So the fastest way is not the fastest way now. It's the fastest way now, and then you move a bit, and it's the fastest way then. So it's very gradual. And this requires a lot of computation, even for normal machine learning, normal processing, AI processing. It takes a lot of, computation. And quantum can actually help you with that to be much faster. Things like using things related to health. So to be able to, analyze if someone has cancer, which requires you to analyze an image like a few hundred times to analyze all of the different levels, of a scan of an image, like a CAT scan or something like that, right? And after a while, you will be able to find things better and more detailed if you have more computational capacity, more time to read things. And quantum can help with that. So I did mention traffic management, machine learning, generic machine learning for data, like tables of data. You want to learn from things, the same you already have in normal computing, but you want to do that in quantum. There's already some libraries for you to do machine learning with quantum already, okay? So you can already try some of this, okay? Yes, you can do Skynet, of course, but there's another thing that I wanted to mention, which is cryptography. So with quantum, things are much faster, so you'll be able to hack cryptography, which is actually not very good, okay? So it will be a bit more complicated for you to guarantee cryptography if someone can hack things. So instead of taking like 10 years to hack your keys, they will be able to take, I don't know, 2 hours or something like that, right? For a small, conversation that we have here for 1 or 2 hours, after 1 or 2 hours, the key is going to die from this communication, so we don't have to worry. But in some situations, the keys live for weeks and months to store the information, and that requires problems. You also have quantum cryptography. So specifically, you can share keys from A to B. And the advantage here is because once you try to read the qubits, they become invalid. So that means that the key is lost. So you can guarantee that keys are only read from the source to the destination. And communication is actually only read from source to destination. There's another logic here, which is you can actually have pairs of qubits that share the same value. So even if they are very far apart, and this is something people haven't explained, even if they are farther than this, the communication goes instantly, even faster than the speed of light. So there are still some uncertainties in terms of physics that we don't know how to explain yet, but probably someone will, but this actually happens. So we can communicate if you have bits in different places, know which value each has. If it is one value on one side, it's the same on the other. So there's a lot of chances process for communication, which actually go much better than fiber, because, you know, you can have one of those bits on your watch, pair them, and then you actually have someone else using this as well. Okay, so this works really well as well. Okay, let's mention, so cracking cryptography is something that I mentioned already, and we have limited time, so let's move on very quickly. So let's say you have bits. Bits are zeros or ones. Sometimes you have the non-existence of a connectivity in terms of the actual physical cable. So it's a three-state or disconnected. So we just have these kind of values. But if you have a qubit, you have much more values. You have multidimensional information about the bits, okay? And that's, I'll show you this just in a second, okay? I also want to mention that, you know, coming from what we've learned so far, that's when you have a normal computer, you know, you grow from machine learning instructions or then assembly, and then you have some operating system, you have some libraries, some drivers, etc., all the way up to higher level programming languages that you use, let's say C# or anything graphical that you have that shows images on Windows or on Linux. And that requires, you know, thousands and thousands more complexity than just a simple hello worlds that you use in assembly. Or if you try to use it, for instance, in quantum, it will actually require very basic amounts of qubits. But then, you know, if you try to complicate things, it grows bigger. So all of these libraries, all of these layers that you have in the middle are relevant, and some of these are already built. So we don't have to go all the way down. We need to understand what's down there, like the same way we understand bits and we understand basic instructions. But then, you know, you have some nicer libraries that we can just use those, and that makes it simple. And there is one called Q#. So basically it's a language for quantum, similar to C#, okay? Now, I have a few links here, okay? And I will show you just one or two, and these are my last set of links, except one other slides, but I will get to that in a second, okay? So very quickly mention that, and these links are basically Wikipedia, okay? So if you go here, you'll actually see that the qubits look, in this case, three-dimensionally. So this is a very easy thing to do. So let's say 1 is on top, or actually 0 here is on top, 1 is in the bottom, okay? And they actually have this weird name, this weird notation, in which a 0 and 1 look like this. They call them the Dirac or bracket notation, okay? But if you try to see them as, you know, vectors, or if you prefer as matrices, it's a 1 and 0 here because it's more than one dimension, and it's a 0 or 1 here for the 1. And then you can do operations. So if you mix the two together, they look slightly different, but you can do operations with some of this. And remember that these are not really absolute values. These are probabilities of values. So that's the uncertainty part that I mentioned. Now, I don't want to go into a lot of this math, so feel free to read it if you want to, okay? But I'm just going to mention a few logic gates, you know, similar to ANDs and ORs, but these are slightly different because remember, every time we read them, we lose the states from the original bits. So that's something to worry about, okay? So we have a few of this. If you go to Wikipedia quantum logic gates, we see a few of these, okay? I'm not going to mention all, just going to mention one or two, okay? So let's say if you have polygates, and you can see that some of these are just the inverse of the other. So if you have a 1 with the polygates called X, so there's a polygate called X, another one called Y, another one called Z, you know, they had no better names. But in any case, this one is the inverse of the other one. So that means that whatever was 1 becomes 0 and vice versa. And then you have a few others that just change the position of the vectors, right, in real world space, right? So they point to a slightly different place, even though they can still have a 0 or 1, they point slightly differently, okay? And this is the example of the Z vector here. Okay. In any case, a few of the ones I wanted to mention is controlled gates. Anything that says controlled gates, you have two bits, okay, qubits. One of them just controls, the first one typically just controls if you apply the operation or not. And the second one is the bit where you want to do the operation. So let's say you have a qubit that says controlled NOT gates. And the operation is just as simple as this. The first bit never changes, okay? So if the bit is 0, the bit on the other side doesn't change either, because this is like a chip select or, you know, something like that when you have in electronics. But if the first bit is to 1, so that means enabled, let's call it like that, the other bit actually applies the NOT operation. Okay, so anything controlled means that the first bit, typically by convention, the first bit actually has an enabled or disabled option, like a chip select, that allows you to apply that operation or not apply anything at all. Okay, and there's a few. There's also other ones like XOR, etc. There's a few options here. I just want to mention one or two which are interesting. Okay, and the Hadamard gate is great for a lot of different things, including cryptography. What does this do? Well, you actually requests, you have a qubit, you apply that gate, and then the result is that you get some uncertainty. You have 50%, 50% of chances of being a 0 or a 1. And that's your best random, okay? Modern computers can only do random based on, current time or something like that. This is real randomization, 50%, 50%, okay? So you can apply, random bits, generate random bits for cryptography or something like that, which is very easy. There is more like swapping the value of two bits, etc., and a few others. Some of these become more complex. You have the truth table here, probably simple to read than just the matrix itself, okay? But you do have a lot of interesting information, but I won't go into too many details at this moment, okay? Now, a few things to mention. When we talk about Azure and how Azure can do this, if you go to docs.microsoft.com/Azure/quantum, you have a lot of information how to get started. So first of all, you need to set up Azure Quantum on your computer. This is very easy. And then you need to do random number generator example, for instance, or a few others. There's many more. Now, I'm going to show you this. So this is my Azure portal here. Down here, I've actually created, you can go to the plus sign here on the left and actually say quantum. Okay, and then you have Azure Quantum. You have other quantum options, by the way. This is not the only one. And then you can just say create. This is easy. You fill in some very quick information about the name that you want to give that instance of quantum workspace, etc. You tell how you want to pay for it, the usual stuff. By the way, you can get a free account if you go to azure.com/free. If you are students, go to azure.com/free/student or students, something like that. And you can even get that for free as well. And then you can try this out. So basically you have to select the region, and only about 10 of them exist at this moment out of 60 in total, but this will increase in the future. I am somewhere in Europe, so West Europe is my best guess for this, but someone else might use a different location. Anyway, when you have a quantum workspace, so in the end, I'll actually press the button to create it, but this has been created already. You can actually go here, and I do apologize for not giving you a bigger demo, but any demo here in half an hour will take too much time, but I will explain how this works. So you enter the quantum workspace, and then you are able to go here to quantum computing quick starts. They will explain what to do. So you go and create, you go to Visual Studio Code, you can use other tools, and then you need to install some extensions, QDK, Quantum Developer Kits. So, you have SDKs for a lot of things. This one is for quantum, okay? And then you need to install a few other things related to Azure, Azure CLI. Everyone uses that when they use Azure. And then you can download some samples, etc. And for instance, this sample is first computing job. So you try it out. And this one generates a sample that you can try out. So if I'm not mistaken, this is the randomized sample, which is okay. But you have others as well. Okay, so you can also do a few others using, the first one is okay, but you can do others with IonQ or Honeywell. And what are these? Well, you have providers. Now, by default, you have a provider which is Microsoft's, but you can add more providers. These are the people who actually have the computational capability for you to run the quantum. And at this moment, you have Microsoft, and you have Honeywell, and you have IonQ. And you also have here 1Q Clouds, which is okay, but let me give you the prices for this. So if you go to Honeywell, this becomes very expensive. So don't be scared. It's in the standard version is 125,000 per month. Okay, so that's a bit, but the other one is a bit cheaper, okay? So try the Microsoft ones if you'd like. So those are much cheaper. But this one, for instance, if you select pay-as-you-go, the cost is actually not expensive. So on a starting point, it's actually cheap. However, you will need to start by by paying. So the free tier that you have does not do this any good. And you can see that running one gate, oh, it costs this amount of money. So it's very cheap, but then you add more and more and more, and it becomes much more expensive, okay? So these are just a few examples for you to try, okay? And anyway, there was another part, and obviously we don't have time for this, but here's just a few links. This will be recorded, so you will be able to pause the video later on to see these links. And most of these are easy, but there's also a few links, and this is not my slide, okay? The person who created the slides in January, if I'm not mistaken, is here, works for Microsoft, and this is a slide that I stolen from a quantum session some time ago, and it has very nice links. So some of the links are repeated from the ones I mentioned, but you have things like GitHub, you can go to quantum libraries, machine learning including, etc. But you also have the online workshop. So just go to this workshop. It's about 5 or 6 hours, give or take, but you learn a lot more about how to do this. So mine was just a very quick introduction, what you can expect from quantum. But if you go to this workshop, it's free, just go there. You'll actually learn a lot more how to prepare and how to play around with this for the first time. So that would be my recommendation, aka.ms/AQDW, something similar, but play around with this. This will be very fun, okay? By the way, same way as machine learning was the future 5 or 10 years ago, this is the future now, okay? So, you know, in a few years, people will start to use this a lot, okay? So anyway, just to mention, last question. So I know it's very difficult for people to be able to interact here, sadly, but feel free to try to answer this. Is the cat going up or down on the staircase? I'm not going to give out the answer, but feel free to write in the comments what your opinion is, and especially why. And why is always important when you do any kind of scientific, you know, declaration, okay? You have to explain why. Explaining is always important. Anyway, for me, that's it. I really want to thank everyone for being here. Also thank Vivian for being here just before me, and also to the organizers. So Jay, Salisha, and everyone, thank you very much for having us.
So good evening. Good evening, ladies and gentlemen. Once again, I would like to thanks to our speakers for delivering such a wonderful program. I thoroughly enjoyed the program, and I believe that our participants and our listeners have a great learning opportunity from our today's session. Meantime, I would like to extend our gratitude to our supporters, and our today's supporters are Microsoft Inc., Blink Ventures, and ICT Awards. We hope that you enjoy listening our program, and we certainly look forward to coming up for next time with another content. Until then, have a great time. And André and Vivani, we are more than grateful to both of you for accepting our invitation and being here with us and delivering such a wonderful program. More than grateful, and thank you so much.
Okay, thank you very much. See you next time. Thank you for having us.
Thank you. Thank you everyone for joining us.